Welcome to the second part of the recording, functional groups and reactivity. In the first part of the video, we talked about functional groups, and we divided them in levels according to the number of bonds that the carbon in the functional group had to heteroatoms that were more electronegative than carbon. In the second part of the video, we are going to be looking at how to move from one functional group from one level to another. So how we can move from a functional group in one lower level to a higher one, or the other way around, from a higher level to a lower. I will start sharing my presentation right now. This is a reminder, this session and the previous video are based on a chapter from Chemical Structure and Reactivity and Integrated Approach by Killer and Wathers. You have the scanned copy of this chapter available on Blackboard. The first part of the video focuses on classifying a range of functional groups according to their level, and we'll study different functional groups at levels 1, 2, 3, and 4. This video is going to be looking at the ways to transform functional groups within the same level, and also appropriate synthetic routes that will allow us to move up or down functional group levels. And quite a few of the reactions that we're going to introduce today, we will pick up in future sessions throughout the module. So this is just a potted overview of what the organic part of this module is going to contain. So how do we change functional group level? Well, when we are moving down a level, we need to form or a new carbon-carbon bond or a new carbon-hydrogen bond. And that new bond that is formed is at the expense of a carbon heteroatom bond. So for example, if we imagine a carbon atom in a carbonyl group, that carbonyl group is a level 2, and we want to go down, let's say, to level 1 and form, for example, a hydroxyl group, an alcohol. Then we would need to reduce that. We need to use a reducing agent because we are forming a new carbon-hydrogen bond. The bond I haven't drawn here would be to a hydrogen. However, if instead of doing this transformation, we were thinking of, again, we have a carbonyl group, but this time we want to, move it again to a level 1 group, but let's say add another carbon-carbon bond. Then we cannot do it just with a reducing agent. That would only increase the amount of hydrogen in the molecule, but it will not add carbons. We will need to have a nucleophile. We will require a reaction with a nucleophilic carbon. When we move up a level, then the molecule, the functional group, will be losing or a carbon-carbon bond or a carbon-hydrogen bond in order to form that new carbon heteroatom bond. So imagine we go, instead of from a carbonyl group to a hydroxyl, we go the opposite direction, from the hydroxyl to the carbonyl group. And in both cases, we are either losing or the hydrogen, or in this case, this carbon group. Losing that carbon-carbon bond or that carbon-hydrogen bond will require the use of an oxidizing agent. These are some examples that we will explore in future sessions in which reductions, in which we use reducing agents, in which reductions are taking place. So if you focus on the carbons that have a number, the ones with a red dot that have a number in red, you will see that in all cases, they move 1 or 2 functional group levels down. So for example, and it's all using what we call reducing agents. And we will be looking at sodium borohydride, lithium aluminum hydride, etc. in future sessions. So this is just an overview of the type of reaction we need to do. We are moving from a higher to a lower level, we need a reducing agent, because we are not forming a new carbon bond. As you can see, there are new hydrogens that are being added to the molecule, and they're the ones highlighted in a sort of greenish, bluish color. In this slide, we have the example of when we are making a new carbon bond. So, for example, in the first example, we have and we use a nucleophile. So here again, we have the carbonyl group. We have a functional a group in a level 2 functional level, and we reduce it to a level 1 functional level. But we have not only reduced the level, we have added a carbon bond to our structure. And as you can see, all the reactions in this example contain that sort of transformation, either one level, from a level 2 to a level 1, or even up to 2, down to functional levels. For example, in the example in D. But in its case, in all the cases, we are using a nucleophile, a substance that will give us that additional carbon bond that we are forming. And this is an example of how we can use oxidizing agents to go up 1 or 2 functional levels. And you've got here, for example, potassium dichromate, we've got potassium permanganate. Some of them are quite common oxidizing agents, others like PVC perhaps are less common. And as you see in all these examples, we are moving either 1 or 2 levels by the means of an oxidizing reaction. And again, we will have a session, we were going to have a session in which we'll be looking at reducing agents. We will have a session in which we look at oxidizing agents, and we will have a session in which we will look at this use of a nucleophile to add carbons to our molecule. So as a summary, to move down a functional group level requires either a reducing agent if we are forming a new carbon-hydrogen bond, or a nucleophilic substitution to form a new carbon-carbon bond. And that will happen at the expense of a carbon heteroatom bond. In this case, the X is not only a halogen, it's any heteroatom. Think oxygen, nitrogen, phosphorus, sulfur, halogens themselves. When we're moving up a functional group, and we need to use an oxidizing agent, and what we are forming is a new carbon heteroatom bond. And that new bond that we have formed with that heteroatom is at the expense of a carbon-carbon or a carbon-hydrogen bond. So at the bottom of this slide, you have an example of 4 different transformations on functional groups. And I'm going to ask you to identify in the carbon that has the red dot, first of all, which group level that carbon is, both in the reagent and the product. And second, what kind of reagent would you use for each of the transformations? Would you use a reducing agent? Would you use an oxidizing agent? Or would you use a carbon nucleophile? As an example, I'm going to do the first one. So we've got here this transformation, and the reagent is a ketone and the product is an alcohol. And if I look at the functional level, functional group level, I can see that that carbon double bond oxygen, that's a level 2 group. And in this case, the product, the alcohol, is a level 1 group. So I'm moving from a higher to a lower functional group, from a level 2 to a level 1 functional group. So what would be the best reagent that would give me that transformation? Well, because I am reducing functional group level, because I'm going from a higher to a lower functional level, then I have 2 options. I can either use a nucleophile if I wanted to make a new carbon-carbon bond, or I could use a reducing agent. And the structure doesn't show any additional carbons, doesn't show anything, the skeleton structure doesn't show anything different. So then that means that here what my structure has gained has been a hydrogen atom at the expense of having a bond of one of the bonds that the carbon had with the oxygen. So that means that for this transformation to occur, I will need to use a reducing agent. So now, this is an example of what you would be doing with the other three reactions. So I'm going to ask you to go back to the previous slide and look at the other three examples and work out what type of reagent will you use for those transformations. And you might even want to go one step ahead, one step beyond that, and not only suggest reducing agent, oxidizing agent, or nucleophile, but perhaps even suggest what reducing agent you might want to use, looking at previous examples from the previous slides. For example, here, perhaps sodium borohydride, or lithium aluminium hydrate. That's not really necessary for the exercise, because we will be looking more into detail in the future sessions at those specific reactions. So at the moment, if you feel comfortable enough suggesting a particular reagent, then that's great. But if you just want to focus on reducing agent, oxidizing agent, or nucleophilic carbon, focus on those three options. Another interesting type of transformations is the carbonyl addition reactions, and it moves level 2 to level 1 functional groups. And all these carbonyl addition reactions are based on the attack, the nucleophilic attack of the carbonyl bond, of the pi skeleton of the carbonyl bond. So if you remember a little bit from your previous chemistry studies, you've got this carbon with a strong partial positive charge, this oxygen with a strong partial negative charge, an oxygen that is capable of stabilizing, and both a partial negative charge, but a real negative charge if necessary. And the attack of the nucleophile, represented here by the X, to this carbon with a strong partial positive charge, results in that first structure, in which the new fragment of the molecule, the nucleophile, has attached itself to the structure. If the nucleophile is an electronegative atom, if it contains, for example, nitrogen and oxygen, then the functional group remains at level 2. As you can see here, now if that X is an oxygen or a nitrogen atom, the structure, that carbon would still be a level 2 carbon. And it might be possible for the pi bond to reform. And I've got an example in the next slide. So here, for example, if the nucleophile is a carbon or a hydrogen, in here you've got a carbon with a negative charge, the cyano group, then the functional group level drops from 2 to 1. And if you look at it, here is the carbon, the one that has this negative charge and attacks the partial positive charge of the carbonyl group, the carbon from the carbonyl group. And then just a simple capture of a hydrogen from the medium, and you form this acetone cyanhydrin. The interesting point of this compound is that it can revert back to the formation of a carbonyl group, and it's a testament to the strong and very stable bond that carbon double bond oxygen can form. The strength of the carbonyl group as a very resilient structure, which can often bounce back from a reaction and recover, and that carbonyl group be recovered. So for example, here, in the presence of, let's say, a base, for example, something that is able of capturing the hydrogen from this hydroxyl group and leave the oxygen with a negative charge. And then, as you can see, the carbonyl bond quickly reforms. And the group that has been liberated is the cyano group. And actually, this is a nice way of generating in situ cyanides. So just a brief summary of some of the things that we have looked at. We have looked in the first part of the video to the functional groups and the presence of heteroatoms and how the type and number of heteroatoms determine the behavior of the organic compound. Different arrangements of atoms in a structure, in an organic structure, we call the inner repeat that repeated over and over again in different molecules are called functional groups. And typically the carbon skeleton of a molecule is less reactive and often will remain unchanged during a organic reaction, and what will change is the bonding to the heteroatoms, so the type of heteroatoms present in the molecule. And if your molecule contains double and triple bonds, if it has a pi skeleton, then especially if they're conjugated systems, for example, aromatic systems, and we have a session on aromatic compounds, then that pi skeleton is relatively reactive and can be used to introduce more functional groups in a molecule and transform those functional groups in that molecule. It is relatively easy to move within the same functional group level by just swapping one carbon heteroatom bond for another. And typically water, potentially with hydrogen ions or hydroxyl ions, you can have that sort of transformations. For example, most level 1 functional groups tend to hydrolyze to form alcohols. Level 2 functional groups form aldehydes or ketones. Level 3 will form carboxylic acids, and level 4 ones will form CO2. And we saw an example of that in the first video. So I will stop the presentation now. So I hope this was useful. The book chapter itself covers this in much more detail. So please do read it and ask me any questions you might have, either in the chat, in the discussion board, or by email, or in one of the sessions we are going to have together. And the presentations, these 2 videos, are I'm hoping to give you an overview of the key points that you need to concentrate when working your way through the chapter. Thank you very much for listening. I hope it was useful, and see you soon.